There's certainly diffraction gratings which are not at all accidental, and perhaps the most relevant for the biological sciences has been X-ray diffraction. In the 1920s, X-ray diffraction became developed as a tool for understanding the structure of crystals. You take an X-ray tube and you form a beam from a hole in a lead screen or something, and then the beam hits some crystalline solid. And the spacing of the atoms in the crystal reflect they form different planes in space, and those planes are separated by distances which are of the order of the wavelength of X-rays. X-rays have very short wavelength, on the order of a nanometer, a few nanometers. And so what happens is the X-rays diffract off the pattern of the atoms in the crystal and appear on a far screen or photographic plate as a pattern of dots. And from the pattern of dots, you can figure out the interatomic spacings of the crystal and even the crystalline structure. And as time went on, from the 20s to the 30s to the 40s, more and more complicated crystal structures were unraveled using X-ray crystallography. You get some material like a protein, and you can crystallize it so that all the protein molecules are lined up in a certain direction, and then pass X-rays through it. You can get an X-ray pattern that corresponds to the interatomic spacing in the crystals. And some really brilliant people then figured out the various structures that occur in proteins, including these spiral structures. Well, of course, the big one to figure out by the late 1940s was what is the structure of the DNA molecule itself. They knew DNA was very heavy, that it was some sort of long chain type molecule, but it was Watson and Crick that figured out that it was something that we now call the alpha helix, which I'm sure you're familiar from your bio courses, biochemistry courses. And this was much to the chagrin of Linus Pauling, who was hot on the trail of this, really trying to figure out what is the structure of DNA. And he got stuck, Linus Pauling did, with his own idea, which turned out to not be the correct idea, and Watson and Crick figured it out. On the other hand, there is the notion out there that Watson and Crick, to do this, didn't get the data themselves. They kind of took, in an unauthorized manner, the data that they ultimately used to figure out the alpha helix structure. So there's been controversy surrounding this from the beginning, but it got a lot stranger as time went on. Of course, Watson and Crick won the Nobel Prize for the discovery of the alpha helix structure of DNA in 1962. And Watson went on to direct the Cold Spring Harbor Laboratory in New York for some years and eventually became president of it, helped establish the Human Genome Project in 1992, finally resulting in the full human genome being sequenced by around 2000, I think it was. But Watson had this long history of very controversial comments of racist and homophobic and anti-stupid people nature. He basically believed in genetic cleansing or something of the human population. Go read some of the things he said. Eventually it got so bad that he could no longer maintain his position as the president and director of the laboratory, and in 2007 was forced to resign. And then just a few weeks ago, the world was treated to the specter of a living Nobel Prize winner being forced to sell his Nobel medal, in this case for $4 million at Christie's in New York. I couldn't believe this when this happened just over a month ago. And it turned out that the guy who bought it was a Russian tycoon who felt sorry for Watson, because what Watson said he wanted the money for was not himself, but to support the laboratory. And so he bought the medal, gave the money to the Cold Spring Harbor, and returned the medal to Watson. Crick had died some years ago. His family sold his medal too. I think it's kind of bizarre to sell your Nobel Prize, but okay. Every dot on this list is a book that could be written, and in a number of cases has. I urge you to go read about it for your own cultural thing. But anyway, that has nothing to do with physics. This does, however, and biology. In my own field, particle physics, we've developed ever higher energy particle accelerators, including particle accelerators that accelerate electrons, which are very light particles. And when you shoot a beam of high energy electrons into a region where you have magnets arranged such that the north and south poles of each magnet here is alternating, north, south, like that, what happens is it wiggles the direction of the electron. And we call these wiggler magnets. And when a high energy beam passes through a wiggler magnet, it's basically shaking off X-ray photons from the high energy electron. And so you get very, very intense beams of X-rays coming out of these wiggler magnets after you shoot a high energy beam of electrons into them. And that is the way that we now produce ultra high intensity X-ray beams for use in mass production X-ray crystallography. You know, there are thousands, millions of biological molecules, the structure of which we would like to know. Proteins, RNA, all sorts of different things. We'd like to understand how they're made. And so this is now, if you go to places like Stanford and Berkeley, where they have two of the biggest, what we call light sources, but in this case the light is X-rays and the source is a particle accelerator. At these advanced light sources, they have like an automated system to put in a sample, shoot it with X-rays, move in the next one, collect the data automatically. The data are sent to a big processing farm, and you put your sample on the conveyor belt, and eventually your data comes back to you sometime later. So if you're a scientist studying, okay, this gene expresses this protein, what is this protein, what is its structure? You can do that using X-ray crystallography if you get a big enough sample and crystallize your protein. There are other methods for unraveling protein and other molecular structures, but by far X-ray diffraction is the one most in use. There are 5 big X-ray facilities in the United States right now. I can't name them all, but you can easily find them online. Europe has several. Japan, China, all have them. It's the thing to do. And in this century of the biological revolution, these are the workhorses for figuring out how all these molecules are structured. And it's based on the mathematics and the physics that you just have learned about so far this morning about diffraction.